The objective of this lecture is to provide the first part of the study of the orbit as a function of time. This lecture focuses on eccentric anomaly as a function of true anomaly. This lecture is divided into the following parts. First, a definition is provided for eccentric anomaly. And then, using this definition, a relationship between true anomaly and eccentric anomaly is derived. Now, a key aspect of this lecture is going to be the geometry of the orbit using concentric circles. Now, these concentric circles, the larger one has a radius equal to the semi-major axis. And the second one has a radius equal to the semi-minor axis. And as we'll see, these two circles serve as a key part of the derivation that relates the true anomaly to the eccentric anomaly and vice versa. So before we get started with this lecture, let's provide an overview of the orbit as a function of time. So until now, the focus has been on understanding the orbit as a function of position. Now that position has been provided using the true anomaly. So the true anomaly, nu, has been used to quantify the location of a spacecraft on an orbit. Now, in addition to location or position, it is also important to know when the spacecraft is at a particular position on an orbit. So that implies we need to know the time. Now, it turns out that the true anomaly is not the easiest way to be able to measure and deal with time. So we introduce a new quantity called the eccentric anomaly. So in order to address the issue of time, or the need to know the time, a new angle called the eccentric anomaly is introduced. Now, the eccentric anomaly provides two pieces of information. One is it provides a relationship with the true anomaly, and the second is that it provides a relationship with time. So this angle, which we will call big E, which is the eccentric anomaly, has these two functions that, using the eccentric anomaly, we can actually figure out the true anomaly, but we can also relate the eccentric anomaly to time. And because we have relationships between all of these quantities at that point, we can actually relate the position to the time, which is the objective of this part of the material. So let's start with the basic geometry of the eccentric anomaly. Now, this basic geometry looks as follows. I'm going to start with a circle. It's a larger circle. And this larger circle has a radius equal to the semi-major axis. Now, tangent to this circle on the inside, at the periapsis and apoapsis, I'm going to put an ellipse. So here's my ellipse. Now, inside this ellipse and tangent at the top and bottom, I'm going to inscribe a second circle. Now you can see from the picture that the larger circle has to have a radius equal to the semi-major axis, while the smaller circle has to have a radius equal to the semi-minor axis. I'm now going to label several points. The center of both circles and the ellipse is going to be C. O is going to be the focus. And now S is going to be the location of the spacecraft. The vector from O to S, where S is here, that vector, of course, is the position of the spacecraft relative to the focus. And point P, which is the periapsis, is going to be labeled as such. Now, the angle between OP and OS is the angle we've already defined. That angle is the true anomaly. I'm going to introduce a new angle now. I'm going to take the point directly above S and on the bigger circle. I'm going to label that point A. And then I'm going to connect C to A. Now, when you look at this connection, you can see that there's an angle now formed between the direction CO or CP, whichever way you want to look at it, and the direction CA. And that angle is called the eccentric anomaly. So E is what's called the eccentric anomaly. Now, given this geometry, you can see that the distance from C to A has to equal A, which is the semi-major axis. And I'm going to label another point here, which is B. B is the point on the inner circle, such that it lies along the direction from C to A. And the distance from C to B has to equal B, where B is the semi-minor axis. So that's the basic geometry that we have here. But in order to finish the picture, because we're going to need all this stuff for later, we know that CO, which is the distance from the center of the ellipse to the focus, that has to equal a times e, because that's the definition of the distance from the center of the ellipse to the focus. So now we have most of the information that we need, and we can actually work our way through the math to be able to figure out the relationship between the distances here in terms of these quantities and in terms of the eccentric anomaly and the true anomaly. So we're going to add to the drawing from the previous page by defining a new point. That point is going to be labeled D. And D is the point that lies along the line from A to S and intersects the direction CP. Now you can see from the diagram that the distance from O to D is equal to R times the cosine of nu. And if I add that distance to AE, which is the distance from C to O, I get the projection of CA onto the horizontal, which is equal to A times the cosine of E. So that's the first relationship. The second thing is you can see that the distance from B down to the direction CP is the same as the distance from S down to the direction CP, because these 2 points B and S are along the same line horizontally relative to one another. So as a result of that, we actually have another relationship, which is that R times the sine of nu, which is the distance from S to D, has to equal B times the sine of E. And we also know that B has to equal A times the square root of 1 minus E squared, because that's the definition of the semi-minor axis. So that means that B times the sine of E has to equal A times the square root of 1 minus E squared times the sine of E. So now we actually have a way of being able to compute the radius as a function of the eccentric anomaly, and that's done as follows, which is that if we move in the first equation, if we move AE to the other side, we wind up with R times the cosine of nu is equal to A times cosine of E minus little e. So now what we can do is we can take the sum of the squares of R sine of nu and R cosine of nu to end up with an expression for R in terms of E. So we then have R times the sine of nu is equal to A times the square root of 1 minus E squared times the sine of E. And we have R cosine of nu is equal to A cosine of E minus little e. So now let's take the sum of the squares. Well, we get R squared sine squared nu plus R squared cosine squared nu has to equal A squared, which comes out of this whole thing, times 1 minus E squared sine squared E plus cosine of E minus E squared. And that implies that we have R squared and then we have sine squared plus cosine squared, but that's just equal to 1. So the left-hand side becomes R squared. The right-hand side becomes A squared, and now we're going to do some expansion, which is we have 1 minus E squared times sine squared E. And the second term, when we expand it out, gives us cosine squared E minus 2 little e cosine of E plus E squared, which is then equal to A squared times sine squared E minus E squared sine squared E plus cosine squared E minus 2e cosine of E plus e squared. Now we note that in this last expression, sine squared e plus cosine squared e is equal to 1. So we get 1 minus e squared sine squared e, because the sine squared and cosine squared become 1, and we still have the e squared sine squared e, minus 2e cosine of e plus e squared. Now what we can do is we can substitute in for sine squared e. So this gives 1 minus e squared, well, sine squared e is equal to 1 minus cosine squared e. And then we have minus 2e cosine of e plus e squared, which is then equal to a squared. And if we look at these expressions, we've got 1 minus e squared plus e squared cosine squared e minus 2e cosine of e plus e squared. Now notice that in this last expression, the e squared and the minus e squared cancel out. So we wind up with a squared times 1 plus e squared cosine squared e minus 2e cosine of e, which can be written as a squared times 1 minus 2e cosine of e plus e squared cosine squared of e. Now this last expression that's in the square brackets is actually a perfect square, which can be written in the following way. So then r squared is equal to a squared times 1 minus e cosine of e, the whole thing squared. That's the perfect square. Now, because r has to be bigger than 0, because it's a radius, the positive square root is the only one that matters. We wind up with r is equal to a times 1 minus e cosine of e. So that's a relationship now for the radius in terms of the eccentric anomaly. Now recall from earlier, we had that r times the cosine of nu was equal to a times cosine of e minus little e. But now we have an expression for r, so we can substitute that expression in, and we get a times 1 minus e cosine of e times the cosine of nu is equal to a times cosine of e minus little e. So if we solve this for the cosine of nu, we get that the cosine of nu is equal to cosine of e minus little e all divided by 1 minus e times the cosine of big E. So that's a relationship for the cosine of nu in terms of the eccentric anomaly. Now what we're going to do is we're going to take another step, which is that we're going to derive an expression for the sine of nu, and we're going to actually use these two expressions together to be able to figure out a nice compact relationship between the true anomaly and the eccentric anomaly. So given that we have the cosine of nu, we know that sine squared nu is equal to 1 minus cosine squared nu. So that means that this has to equal 1 minus this whole thing that I've just derived, cosine of e minus little e, all divided by 1 minus e cosine of e, this whole thing squared. So now let's take that to the next page and let's manipulate it. So the last expression can be written as sine squared nu is equal to 1 minus e cosine of e all divided by 1 minus e cosine of e, the whole thing squared, minus cosine e minus e all divided by 1 minus e cosine of e, the whole thing squared. Now if I put this over a common denominator, the denominator is 1 minus e cosine of e squared. The numerator is 1 minus e cosine of e squared minus cosine e minus little e squared. Now we're going to manipulate this last expression. So this last expression becomes, when I expand out the numerator, I wind up with, I'm going to leave the denominator alone here, cosine of e squared. So I get 1 minus 2e cosine of e plus e squared cosine squared e minus, and I get cosine squared e minus 2e cosine of e plus e squared. Now this expression can be rewritten as follows, which is, I've got 1 minus e cosine of e squared in the denominator. Now you'll notice that I have a minus 2e cosine e, which cancels with the 2e cosine e after I distribute the negative sign. So I wind up with 1 plus e squared cosine squared e, and then I have minus cosine squared e, and then I have minus e squared. Because as I said, the 2e cosine e cancels out. Which then leaves me with, now you'll see that there are terms here that don't involve cosine squared, and there are terms that do involve cosine squared. The terms that don't involve cosine squared just leave me with a 1 minus e squared. The terms that do involve the cosine squared, I can factor out the cosine squared, and I can also factor out the negative sign, and I get minus 1 minus e squared cosine squared e, all divided by 1 minus little e cosine of e squared. So that's sine squared nu, right? But if you look at this last expression, I can factor out the 1 minus e squared out of the whole thing, and I wind up with 1 minus e squared, and then I have 1 minus cosine squared e, all divided by 1 minus little e cosine of e squared. But you'll notice that 1 minus cosine squared e is just equal to sine squared e. So as a result, we wind up getting the following result. So we have sine squared nu is equal to 1 minus e squared times sine squared e, all divided by 1 minus e cosine of e squared. So that implies that the sine of nu is equal to the square root of 1 minus e squared times the sine of e, all divided by 1 minus e cosine of e. So recall now that the cosine of nu was equal to cosine e minus little e, all divided by 1 minus e cosine of e. So now I have an expression for both the sine of nu, which I just derived, but earlier I had the expression for cosine of nu. So I can use these two relationships together, but I need one other thing, which is I need an identity. And that identity that we're going to use is going to be as follows, which is that from trigonometry, we have that the tangent of nu over 2 is equal to 1 minus the cosine of nu, all divided by the sine of nu. This is just a trigonometric identity. So what I can do is I can substitute these expressions for sine of nu and cosine of nu that I have into this expression to be able to simplify this in terms of the half angle nu over 2. And that works as follows. So we then have that the tangent of nu over 2 is equal to, well, in the numerator, I have 1 minus cosine big E minus little e, all divided by 1 minus little e cosine e. And in the denominator, I have the square root of 1 minus e squared times the sine of e, all divided by 1 minus e cosine of e. So this last expression can be rewritten as follows. Well, I can put in the numerator, I can put the whole thing over 1 minus e cosine of e, and I get the following result, which is I get 1 minus e cosine of e, all divided by 1 minus e cosine of e, minus cosine e minus little e, all divided by 1 minus e cosine of e, and that's going to be divided by the square root of 1 minus e squared times the sine of e, all divided by 1 minus little e times the cosine of e. Now, of course, you can see that because I did that, that gives that the tangent of nu over 2 is equal to, well, because I have a common denominator in the numerator, and it's the same as the denominator of the denominator, the 1 minus e cosine e cancels out, and I wind up with 1 minus e cosine of e minus cosine of e minus little e, all divided by the square root of 1 minus e squared times the sine of e. But this last expression, again, you can see that there are two terms involving cosine, right? And I have a 1 plus e when I actually distribute this negative sign. So I got 1 plus e, and then I have a subtraction of 1 plus e times the cosine of e. So let's actually put that on the next page. So then, the tangent of nu over 2 is equal to 1 plus e minus 1 plus e cosine of e, all divided by the square root of 1 minus e squared times the sine of e, from which I can actually factor out of the numerator a 1 plus e. So that gives that the tangent of nu over 2 is equal to, well, I get 1 plus e, which factors out, and I'm left with a 1 minus cosine of e. And in the denominator, I've got the square root of 1 minus e squared times the sine of e. Now, if I factor out all these coefficients, I get 1 plus e, all divided by the square root of 1 minus e squared times 1 minus cosine of e, all divided by the sine of e. But this factor that involves the eccentric anomaly is just equal to the tangent of the half angle of the eccentric anomaly from the identity I gave earlier. And this other factor becomes as follows. So I get 1 plus e all divided by the square root. Well, 1 minus e squared is 1 plus e times 1 minus e. And like I said, 1 minus cosine e over the sine of e is just equal to the tangent of the half angle of the eccentric anomaly. So when I'm done with this algebra, we get that the tangent of nu over 2, well, 1 plus e over the square root of 1 plus e is just equal to the square root of 1 plus e. So you wind up with the square root of 1 plus e over 1 minus e times the tangent of e over 2. Well, you see it's a nice, simple result. Now what we're going to do is we're going to invert this. Now this inversion is very important that it's done correctly. All right, so what I'm going to do is I'm going to break this up into sines and cosines to be able to do the inversion. And it's going to look as follows. So we can then write that the tangent of nu over 2 is equal to the square root of 1 plus e times the sine of e over 2, all divided by the square root of 1 minus e times the cosine of e over 2. And I did that deliberately because by writing it this way, I wind up being able to break this up into a sine part, or a numerator, and a cosine part, which is a denominator. And I can use the 4-quadrant inverse tangent to be able to invert this. So as a result, if I use the 4-quadrant inverse tangent, we wind up with nu over 2 is equal to tangent inverse of, well, it's of the numerator, which is the square root of 1 plus e times the sine of e over 2. And then the denominator is the square root of 1 minus e times the cosine of e over 2. Now remember, the tangent inverse has two arguments, and it is the 4-quadrant inverse tangent. Now, because it's the 4-quadrant inverse tangent, let's do a little analysis on this just to make sure that we got this correct, which is that you'll notice that e must be on 0 to 2 pi. So that implies that e over 2 is on 0 to pi. So that means that this half angle is in the first and second quadrants. Now, given that it's in the first and second quadrants, that means that the angle nu over 2 is going to be on 0 to pi, which implies, once I multiply by 2, that nu is going to be on 0 to 2 pi. So this actually works out very nicely. So we can actually write the angle nu in terms of e directly from this last result. So we then obtain that nu is equal to 2 times the 4-quadrant inverse tangent of the square root of 1 plus e times the sine of e over 2 and the square root of 1 minus e times the cosine of e over 2. And as I said previously, the quadrants work out because of the fact that we're dealing with a 4-quadrant inverse tangent. So now what we can do is we can do the inverse calculation. So if we perform the inverse calculation, we have that the tangent of e over 2 is equal to the square root of 1 minus e over 1 plus e times the tangent of nu over 2. I just basically multiplied across by the square root of 1 minus e over 1 plus e, from which we actually can write that the tangent of e over 2 is equal to, well, in the numerator we'll have the square root of 1 minus e times the sine of nu over 2, and in the denominator we'll have the square root of 1 plus e times the cosine of nu over 2. And from this, we get that e over 2 is equal to the 4-quadrant inverse tangent of the square root of 1 minus e times the sine of nu over 2 and the square root of 1 plus e times the cosine of nu over 2. And then multiplying by 2 gives us that e is equal to 2 times the 4-quadrant inverse tangent of the square root of 1 minus e times the sine of nu over 2 and the square root of 1 plus e times the cosine of nu over 2. So if we look at these two relationships, they look very similar to one another. The first one gives us an expression for nu in terms of e. The second one gives us an expression for e in terms of nu. So either way, if I know the eccentric anomaly, I can compute the true anomaly. If I know the true anomaly, I can compute the eccentric anomaly. Now, the reason that this becomes important is because ultimately we're interested in orbital elements. So even though we may be doing calculations with the eccentric anomaly, ultimately we want to know what's happening on the orbit in terms of the true anomaly. So the reason that we use the eccentric anomaly is because it provides for us a way to be able to deal with time. And we haven't gotten into time just yet. This is the first part of this discussion of the orbit as a function of time. But before we can actually get into that, we have to develop a way to be able to transform between eccentric anomaly and true anomaly. And the results that we've developed in this lecture provide us a way to be able to do that. So that's basically where this lecture is going to end, is just to be able to derive the relationships between eccentric anomaly and true anomaly, and vice versa between true anomaly and eccentric anomaly, so we can go back and forth. So now we can provide a summary. So this lecture really had two parts to it. First was that a definition of eccentric anomaly was provided. And then using that definition of the eccentric anomaly, a relationship was derived between true anomaly and eccentric anomaly. And of course, as was mentioned earlier, is that the key aspect of this derivation was using the geometry of an orbit. And that geometry involved the use of two circles, which was an outer circle of radius A, where A was the semi-major axis, and then an inner circle of radius B. And these circles were concentric, and we used them to be able to develop a relationship between true anomaly and eccentric anomaly. And this will form the basis of the next part of the discussion of the orbit as a function of time, where we introduce a relationship between the eccentric anomaly and time. So that's the next part, which will come in the next video.